Hey folks, let's see. The other day I mentioned that I wanted to show you, I don't know, not really tricks, but just an overview of the control system designer in relation to Bode plots. So that's what I'm going to do here. I'm going to try to keep it quick, so that you don't have to watch this for an hour or something, but hopefully it has a couple of little goodies in it. Let me bring this little script up. This is a modified version of the one I've used in the past. And it just shows or provides some anonymous functions for doing things like calculating the magnitude and phase angle of a transfer function at a certain frequency, some of the lead compensator equations, and some of the lag compensator equations. You don't have to use these at all. I just might use them. We'll just see how this progresses. Let's make a transfer function. How about this one that we were playing around with earlier today? It looks like, well, you'll see what it looks like in just a second. How about that? So it has a pole at the origin, a pole at 4 or -4, and a pole at -7, and some sort of gain. So we'll take a quick look at this, use the margin command, and we can see we have a phase margin of about 31 degrees. Let's try to do a phase lead compensator, maybe a couple phase lead compensators, so that we get a phase margin of 60. And then what we'll do is, after we get that designed, through a combination of interactions with MATLAB, maybe Control System Designer, then we'll also use Control System Designer to look at the actuator effort, and then throw in a pre-filter. And we'll do all that in Control System Designer. Even though you could do that in Simulink, arguably you could do a better job in Simulink, because you could, instead of using a pre-filter to lessen the actuator effort, you could use, let's say, a trapezoidal input, like you did in lab. So there's a lot of different ways of going about this. I'll try to stay out of Simulink and just use Control System Designer, but I encourage you to use Simulink and explore other ways of shaping that command that is normally a very harsh step. Okay, so back to this thing, phase margin 31. Let's see, we want to get a phase margin of 60. If I look at this thing, well, I'm losing phase pretty fast right here. So let's see what happens. I'm going to ask for 40. And I'll go over here and use some of my cool functions. How about that? Oh, great. That's because I didn't run this thing. Let's run it. Bloop. Okay, now let's use one of the cool functions. Great. So alpha is 0.22. Okay, so let's do the mag drop thing, and we'll throw that in there. So -6.6. Let's see what happens here. I'm going to make this bigger so we can all see it. Maybe throw a grid on it. -6.6. Oh, right about that. Oh, look at that. So I'm going to jot that down. So we have an omega of 4.64. Now, I'm asking for a lot more phase than we need. Even more than 10%. And look what's going to happen when we put our phase bubble right here. We're going to be down. We're going to lose. Let's see, 4.64. We're going to lose, wow, -173. We started here at -149. So we're going to lose 25 degrees of phase. Wow. So I would expect that when we ask for 40, we're starting with 30.6. Let me do some calculations. I'll call it 31. We're asking for 40. We're going to lose 25. So let's see, that's 71 minus 25. So 46. So, we may end up with only about 46 degrees of phase margin. Let's see what happens. I'm going to use, what do we have here? We have alpha we have omega m. I might as well write that in. How about this? Omega m is, what the heck was it? 4.64. And now we can say, I'll call this D1 because we may need a few of these. Make lead, and I have to give it omega and alpha. There is our wonderful compensator. So I'm going to make a new plot. Look at that. I was guessing 46 degrees of phase margin with this puppy, and we get 47. Now, let me show you a little trick. I'm going to make a new plot. And let's plot G, our compensator, and the whole thing. And I'll throw a grid on it. So we're going to have 3 lines now on a nifty little Bodhi plot. This is a nice way to see what's happening. The red is our compensator. We can see the magnitude gain here. There's our phase bubble. The blue is the original plant, and we can see that the phase is coming in there nicely, whereas the yellow is the plant and the compensator. Well, if we move this phase bubble further out this way, this line is going to go like this, and we'll have less gain to eat away at our phase margin. Now, let me bring up this plot. This was our figure 2, which was our compensated system. And we have 47 degrees of phase margin. So I'm going to jot that down and go back to here. And I'm going to do this in a couple ways. I'm going to make a new compensator, but I'm going to call it D1 again. Here it is. And instead of WM, which was 4.64, I'm going to go about 6 instead of 4.64. A new D1. And I guess I'll make a new plot. And let's see what we get for our margin. Check that out. So I pushed the phase bubble to the right. I'm not getting as much of the phase bubble, but I'm decreasing the gain significantly. So I went from 47 degrees up to 52. Kind of a neat little trick. Let me show you another trick. Let's fire up Control System Designer, and I'll just give it G, the original plant. And here is our wonderful Control System Designer. Now, admittedly, we only have 52, degrees of phase margin with this design, so it's not cooked, right? We're going for 60 degrees, and right now, all we have in here is the plant. So here's our original phase margin of 31 degrees. Now, I'm going to get rid of this root locus. Well, I'll leave the root locus in for now. I was going to get rid of it and put in a step response of the actuator effort, but we'll do that later. Well, let's bring in our compensator. What did we call it here? D1. So to bring in the compensator, I'm going to say Edit Architecture. And I looked at beautiful architecture. Here's my plant that's already in there because when I called Control System Designer, I gave it that argument. It just sticks it in G. No matter what I call it, it's going to put it in there. And let's bring something into C. So I'm going to click this little down arrow thing. And this looks at my workspace, and I'm going to pick a D1. I'm going to say Import. OK. And now this Bodhi plot is going to update to our 52.2 degrees. How cool is that? Now, what I can do from a Bodhi plot design standpoint, I can sort of fiddle with my pole and zero of the compensator. I can do that in a couple ways. I can click over here. double clicked, I guess, and it's showing me the real pole and the real zero. So what that is if I were to go pole of D1, that's this. And if I were to say 0 of D1, that's this. Okay, so just, a sanity check that it's doing what we hope it would do. So I could modify those things directly in these fields, but I can also use my magic hand, and grab this 0 and move it. And I can grab this pole and move it. So let's take this 0 and watch this phase margin down here as I move it. I'm going to move it sort of rightward. I'm losing phase margin. I'm going to move it leftward. Still kind of losing phase margin. So the sensitivity of this is pretty much I'm at an optimal phase margin point for that 0. Let's try the same thing with the pole. Move it this way. Oh, I'm getting a little bit more phase margin. Oh, I lost it. I forgot to. Come on. I'll move it this way. I'm losing phase margin. There we go. I'm getting phase margin. So the point here is that sometimes you can do a little bit of tweaking with this. Now what I'm doing from a root locus standpoint is I'm moving this pole further out in the left half plane. Is that a good thing? Well, I can achieve my design here. I'll call this good. I sort of have the design now. But it probably is going to require quite a fair amount of actuator effort. I now have a pole way out here at 26.37. I can't remember where it started. Let's see. It started at 13. I pretty much doubled it. Okay, let's get rid of this plot. I'm going to hit this X and put in a new plot. What I want to do now is investigate how much actuator effort I'm going to need. So what I want to do is show the step response between R in and U out. I can select that up here. So I'm going to say R to U. Plot. Well, is that a lot of actuator effort? I don't know. It starts off at 12, comes down. Let's say that's too much. I don't know how much we can handle, but let's say that's too much. So what do I do with this? Well, if I was in Simulink, I could use that trapezoidal input thing that we used in lab, and that's probably the best way to do things in terms of reducing actuator effort, giving a nice smooth input to the instead of a step. But I can do something crude here. Let's do something crude. So I'm going to say P. I'm going to make a pre-filter. Or how about I do this? Tau equals 0.1. And I'll make a pre-filter that looks like 1, like so. Okay, so I have a pre-filter with a time constant of 1/10 of a second. Why did I pick 1/10 of a second? Well, when I look at this response, this step response here, 1/10 of a second is going to delay things roughly, not 1/10 of a second, but, probably more like 0.2 seconds. So, I'm going to stretch this out a little bit, but it's also going to lower this. 1/2 of a second probably isn't going to, cause me too much trouble here. I wouldn't want to set this to like 10 seconds or something, right? That would stretch this thing way out. Maybe that would be catastrophic. But let's see what happens. So we right now have a peak of about 10 from the actuator, and I'm going to see what happens when we put in a pre-filter whose time constant is 1/10 of a second. Great. How to do that? Go up here to Edit Architecture, and we want to stab it right in here. F. Find F, put the little down arrow, and pick a P. Boop. When I hit OK, things are going to update. Ooh. So we originally had a 10 amplitude, now I only need 2.5. Now keep in mind, if I'm just going to create a random figure here and do a step response of this P, it's really not that gentle of an input. It still has a discontinuity here at time equals 0. Boom! It just doesn't go up like this, it goes up like that. I can smooth that out more if I were to do something like P2 is equal to P times P. Basically, two of those things. Let's look at the step response of P2. That has 0 slope at time equal 0 seconds. So it's a little bit more of an S shape, a little bit more like that trapezoid. But if you were to do a trapezoid on this, you would have an equal S here and here. So a much nicer smoothing type of a situation. But let's see what happens when we go with our P2 in here. So to get P2, I just go back into Edit Architecture and put it into F. And I'll pick P2. Okay, we're here at about 2.4. Let's see what happens. 1.5. Look at that. So we stretched out, no doubt about it, a little bit here. Is that okay? I don't know. It depends what the requirements were. Our phase margin is still 60 degrees, of course. That didn't change. Maybe this is all right. Now let's see. What if I move this back? We'll lose our phase margin. I'm not really looking at these things anymore. I'm just sort of focusing on this. So I'm kind of going back to the design we had somewhere around there. And if I wanted to add in a second lead compensator, I could do that. And I would use this plot to do it. Let's say, what do we have for phi? Let's use the same phi of 40 and alpha of that. And so we'll use our mag drop on alpha, and of course it's the same thing, negative 6.6. So I'm going to start with this lead compensated system, and actually I'm going to do this. What plot am I on? I'm on 2. So I'm going to go figure 3 margin G times D1. I think that's what our compensator was, and we get this. Okay, yeah, this was the original. So now I'm definitely back to its original state, and we're just going to throw in another lead compensator. Asking for 40 seems kind of extreme. We'll do it. So negative 6.6 is, let's see, where's that? Oh, went too far. About there. So omega m is, I'm writing this down, is now 7. All right, and if I go to my cool things here, I guess I'll put in a new omega m. I'm going to make a new lead compensator. Let's call it D2. And omega m and alpha. A new D2. So I'll make another figure. Margin G times D1 times D2. This is both lead compensators, and I have 63.4. So I have lots of phase margin compared to the design requirement that I sort of made up on the fly, which was 60 degrees. Well, let's bring this whole new thing into Control System Designer. So what I want to show you here is that we were in the middle of Control System Designer. I imported a lot of things. Let's clear the slate and bring in this compensator. So I'm going to call this one D1 times D2. So I have capital D in the workspace. Come back here to Control System Designer. And let's clean house. So go into Edit Architecture. I'm going to get rid of the pre-filter. So all I'm going to do is select this and type 1. And for the compensator in C, I'm going to say select capital D. Did I get that 1 in there? I don't know. I think so. And I'll say OK. Well, there's our phase margin that we saw a moment ago on this plot. Or, no, not that one. I don't know where it went. Here it is. No. There it is. 63.4. It's too many plots. We have 2 compensators now. We can see a couple red zeros and a couple of red X's. And we have this response. I kind of like that other one better, but it was a much higher frequency sort of a thing. So, maybe we pay a price for that. Now, in this mode, let's say, I wanted to twiddle with the design a little bit. I certainly could. I could move this one a little bit that way. I'll probably lose a little phase margin. Move this one, back it off in frequency, lose a little phase margin. I kind of like that. We brought our actuator effort down. Did some cool stuff here. I could grab one of these zeros and move it around a little bit. I'm getting some phase margin back. I'm going to need more actuator effort. Okay, the point here is that once you get your baseline compensators into the control system designer, you can fiddle around with it a little bit quite easily. Now, we've seen single compensator. We've seen how to quickly put in a a pre-filter. Now, let's see what happens with time delay. Here's our original plant, and let's make a time delayed plant. And I'll start off by just saying GTD for time delay is equal to the original plant. And now what I'll do is tell it that its input delay property is, 0.05 seconds. And so now we have a transfer function with a time delay. And I can go into Edit Architecture, and instead of G, I'm going to update this to GTD. And when I say OK, heaven only knows what's going to happen, but certainly we're going to lose some phase margin. Maybe it goes unstable. I don't know. Oh my, look at that. So we lost quite a bit of phase margin. We're down to 46. We have this crazy thing going on. We can see the time delay right there, pure time delay. So at this point, I can play around with increasing the time delay until the system goes unstable. So I could make this 0.1. I have a bad feeling about this one. And just go into Edit Architecture and update. I have to reload it because these two things, this thing isn't updating automatically with the workspace, so I have to reload. Ooh, not too bad. 0.1 seconds time delay, and I'm still stable, but only barely. I'm getting a little bit more wiggly. It's telling me I'm getting to the verge of instability. So if we go to, let's go for craziness here. So 0.2. Negative 5.1. Now it's unstable, right? Obviously. So I could play around with some of the compensators. Look at that. I'm getting some phase margin back. I'll move that one up a little bit. And it says phase margin 48.7. Still looks rather unstable to me. It may have gotten confused. Let's see what the compensator looks like. Oh gosh. So I've done some bad things with the compensator as I was fiddling around with these poles. I now have a compensator that has a right half plane pole. So I probably moved something a little bit too much. And let me just make sure that I didn't do something bad here. No, I'm fine there. So what I'm going to do is reload This is good. You can kind of see my hidden freckle. So I'm going to go here to C and reload our compensator, which I call D. And now we're back to where we were. So it should be unstable. And I can go back by reloading the original G. And we should get back to our beautiful phase margin. Look at that. So all was not lost, even though I probably hiccuped or something as I was moving poles around. But there you go. So I think I covered everything I wanted to hit on Control System Designer. I suppose we'll do some Nyquist stuff later. That's really not germane to what you're doing right now with lead compensation. But certainly you can nuke a plot like this, go new plot, and bring in a Nyquist plot if you'd like. And we'll do U to Y. So this is going to be of just the plant here, which makes sense. Sort of the loop transfer function. Look at that. Beautiful looking Nyquist plot. Okay, so we'll end it there. Hope this helps. Bye-bye.